What's up, guys? Today we're going to be discussing mathematical induction. So, firstly, let me just explain very briefly what mathematical induction is. It is a way of proving things, right? Operates on the principle of induction, and it's a way of proving things. So, firstly, before I show you any examples of mathematical induction or go much further into what exactly mathematical induction is, let me first show you this image, like for the sake of an analogy. Let's say we have an infinite number of dominoes, right? This goes on to infinity, and we want to prove that every single one of them will fall, like if under a certain condition, right? So, firstly, you would have to start off by making the first domino fall. You'd want the first domino to fall and then tip the next one, right? We know this intuitively. However, we have to prove it mathematically. So this is like basically an analogy for how mathematical induction works. So the part where you tip the first domino over, that is called the basis step. And the basis step is it's the one in which you show that the first one tips over. The inductive hypothesis, right? Okay. Then next you have to show you choose some random domino, let's call it K, and you show that for any domino K, you want to prove that the next domino, which would be called K plus 1, will also fall over if K falls over, right? Those two steps are called the inductive hypothesis and the inductive step, respectively. The inductive hypothesis is the one where you assume K, and then the inductive step is the one where you assume K plus 1. Or you prove, rather, you don't assume, you prove K plus 1. So let me explain to you why this would make sense. Because, let's just say, assume K and prove true for K plus 1. Oh wait, K is some integer K greater than or equal to some number. Let's just call the number I or whatever. I don't know. Anyway, just greater than some number. Anyway, prove true for K plus 1. Anyway, the reason this makes sense is because for the basis step, if you were to prove that the first one does drop, right, the first one does fall over, then we have proven that if one falls over, then the next one falls over. Then we have that the first one falls over. Therefore, by having proven this, we know that the second one will also fall over because the next one falls over. And then since this one falls over, the third one also falls over. And the fourth one, and the fifth one, and the sixth one, forever and ever. You get me? So that's basically an analogy for mathematical induction. Now, onto an actual example. Let me just, oh my gosh, okay. Let me just delete all this quickly. So this one reads, it says, prove that for 1 plus 2 plus 3 plus 4, all the way up to plus n, prove that can be represented as n plus 1 times n all over 2. I'm sorry, this is from a previous recording of this video. I wasn't happy with how that one came out. So here we are, busy deleting this. Onto an example. Prove that 1 plus 2 plus 3 all the way up to plus n is equal to n times n plus 1 all over 2 for all integers n greater than 0. But what I want you to notice is that n greater than 0 is the same. Integers n greater than 0 is the same as saying integers n such that n is greater than or equal to 1, since 1 is the very next integer after 0. So what we have to start off by doing is the basis step, just how we did it there. So basis step, and we have to prove that 1 plus 2 plus dot 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 plus n is equal to n plus 1 times n all over 2. Prove that that is true for n plus 1. Okay, so we're going to say 1 is equal to 1, okay, because that's this part of the statement. And then now we have to prove this side, right? Remember, to prove it, you can't, by the way, let me just tell you something. You can't just start off by saying, I don't know. You can't just start off by saying that, because then you're already assuming what needs to be proven. So like first you do the left hand side. Left hand side is equal to 1. Right hand side is equal to 1 plus 1 all over 2. And that is equal to 1 times 2 all over 2. Then that's equal to 1, because the 2's cancel, then we're left with 1. Therefore, the left hand side is equal to the right hand side. And therefore, the claim holds true. The claim holds true for n equals to 1. Did I say n plus 1? I meant to say n equals to 1. My bad. Maybe I should just say 1 plus dot 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 plus n is equal to n times n plus 1 over 2 holds true for n equals to 1. Okay, cool. Now, like I said, we have to take some random domino k. Each domino is an analogy for a number here, by the way. You take some domino k, and we assume that it does tip over. Then we're going to try to prove that the next one tips over. That is the inductive hypothesis. And then you say assume. Let me just write a bit bigger so I guess you can see. Assume that 1 plus 2 plus dot 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 all the way up to plus k is equal to k times k plus 1 all over 2. This is extremely important. You have to write for some integer k such that k is greater than 0. You have to write this part, because if you don't, then you're basically saying that it's for any k, essentially, right? It could be any real number k, anything. So it's extremely important to specify that. Then we move on to the inductive step, and this is where we have to prove that 1 plus 2 plus 3 plus 1 plus 2 plus dot 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 all the way up to k. But remember, k plus 1 as well, right? So it's everything leading up to k and k plus 1. So that would of course include k. If k plus 1 is there, then that would include k. Then is equal to, oh, by the way, notice this formula here, or not formula, but that equation there is essentially the same as, it is the same except the k's, or the n's are replaced with k's. It's the same as this original one here, right? And then for the inductive step, you just want to replace all the k's in this one with a k plus 1, right? You can put it in brackets just to show yourself that. So you have to prove that for some integer k greater than 0, right? This is what we want to prove. So I'm just going to underline it, right? The reason I'm underlining it is so that the marker does not think that taking this as the beginning of my proof or whatever. So what you start with saying is left hand side. You could possibly also do right hand side, but the way I'm going to show you is with left hand side. As an activity, you could probably try doing from the right hand side and proving the same thing. So what we must notice here first is that this part here is exactly the same as this here. This here. And we know that by the assumption in the inductive hypothesis that this here is equal to, is equal to k times k plus 1 all over 2. So what we can say is this is equal to k times k plus 1 all over 2 plus k plus 1. And we have to give the reason, so we say by the inductive hypothesis. Okay, so yeah, that's it. Okay, and now we have to continue proving what. So the whole point of this is we're trying to get this equal to that there. So what's helpful is to, like, maybe on the side on a separate piece of paper, or maybe in pencil or somewhere where it won't be marked, you could try to simplify this to get to not to another answer, but to a different form of this, so that when you get to that thing, to the simplified form of this in this equation here, from this expression here, then it will be easier to work backwards. So let me show you what I mean. K plus 1 plus 1 all over 2, that's equal to k plus 1 plus k plus 2 all over 2. And then we can just simplify that. K squared 2k plus 1k plus 2, right, is equal to k squared plus 3k plus 2, right? Okay, so keep this in mind here. I'm just going to put it off to the side. Since I'm not doing this on paper, I have the luxury of just dragging and dropping things wherever I want. So we're going to try to get one of these expressions from this, and then working backwards to get to here. Sorry, I was interrupted. But you're trying to get an expression here from there. So let's just firstly put everything over a common denominator. As we see here, everything's over a common denominator. So you're going to say k plus 1 plus 2 times k, 2 times k plus 1 all over 2. Okay, then we simplify, and then what we're already seeing is that this looks like that. But I guess if you didn't notice, you could simplify all the way to, this is supposed to be plus 2. That's a very common mistake. Don't make it. Anyway, and k plus 1, we simplify, we factorize k plus 2 all over 2. But we want to get it in this original form, right? Because that's the form that we have it in there. So then that's just equal to k plus 2 is obviously just equal to k plus 1 all over 2, and therefore that's equal to the right hand side, right? When we said left hand side, now it's equal to the right hand side. Therefore 1 plus 2 plus k plus 1 is equal to k plus 1 over k plus 1 plus 1 all over 2 for all k an element, for all integers k greater than 0, right? You could say, I guess you could say for any integer k equals to 0. I don't know. Anyway, now you come to the conclusion in which you have to write. I don't know if everyone has to do this, but I am personally expected to in my tests. Oh wait, yeah, I have a conclusion written from the previous video, my previous attempt at making the video. Here's the conclusion. Instead of rewriting it, I'm just going to take this one and drag it up. Therefore, by the principle of mathematical induction, 1 plus 2 plus n, all the way up to plus n, is equal to n plus 1, holds true for all integers n greater than 0. So that is all for mathematical induction for this video, not for all for mathematical induction in general. For this video, in the next video I'll go into further detail and further examples.